Okay, hello everyone. Let us continue. Excuse me. Okay, let us continue the third part of today's class. Okay, before we continue the class, let us see new announcements. Okay, the slides of chapter 3 has been updated, version 20220425B. Hello everyone, I have uploaded the latest version of the slides of chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, slides, chapter 3, slides 20220425B.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of chapter 3 has been updated. Version 20220425B. Hello everyone. I have uploaded the latest version of the handout of chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, handouts, chapter 3, handout 20220425B.pdf. Best regards, Wei Zhen. Okay, next let us continue the course class. Okay, in part 2 of today's class, we have taught to page 52. Excuse me. Okay, now let us see page 53. These SISO channels are sometimes referred to as eigenchannels, and the receiver can decode each of these channels using standard maximum likelihood decoding logic. Okay. I believe that you have learned what is maximum likelihood in the course Digital Communications. Okay, if the professor of the course Digital Communications did not teach you what is maximum likelihood, okay, or you did not take the course Digital Communications, you can write an email to me to ask what is the maximum likelihood. Excuse me. The process of precoding according to equation 3.20. Okay, let us go to equation 3.20. Okay, in equation 3.20, S is equal to V times S tilde. Okay, it is the precoding operation. Okay, let us go back to page 53. And pre-multiplying at the receiver according to equation 3.22. Okay, let us go back to equation 3.22. Okay, in equation 3.22, R tilde is defined as U Hermitian times R. Okay, it is the pre-multiplied received signal by R tilde. Okay, it's called eigenbeamforming. Figure 3.2. Okay, let us see figure 3.2. Okay. In figure 3.2, it is a MIMO system using eigenbeamforming. Okay. In the beginning, there are S tilde 1, S tilde 2 to S tilde R, totally R transmitted symbol. And after the precoding precoder V, okay, that is V times the vector S tilde, we will get S1, S2 to SNT. Okay, they are totally NT transmit antenna. NT transmitted symbols, and transmitted by the NT transmit antennas one by one. And then the signal has been passed through the channel. At the receiver end, there are NR receive antennas, and they received R1, R2 to RNR, okay, totally NR signals. And then it passed through a premultiplier U-Hermitian. That is, we use U-Hermitian to times the vector R. Finally, we will get the received symbols R tilde 1, R tilde 2 to R tilde R. Okay, we call the precoder V and the channel and the premultiplier U-Hermitian together as the effective channel. Okay, figure 3.2 depicts the concept of eigenbeamforming and illustrates the effective channel that is created by the precoding and premultiplying operations. Because equation 3.23, okay, let us go to equation 3.23. Okay, it is the equation R tilde I is equal to the square root of rho times lambda I times S tilde I plus Z tilde I, where I is equal to 1 to R. Okay. Because equation 3.23 shows that each eigenchannel has a gain equal to the square root of the eigenvalue associated with that channel. Okay, let us see equation 3.23 again. Okay, we can see that, okay, for each eigenchannel there is a gain, okay, the square root of lambda I, which is like the channel gain, okay, where lambda I is the eigenvalue of the ith eigenchannel. Okay, we see again the adverse effect of small channel eigenvalues. Okay, that is, the channel eigenvalues should be as larger as possible. Okay, the signal to noise ratio for each eigenchannel rho I is given by rho I is equal to rho times the expectation of the square of the absolute value of S tilde I times lambda I over sigma Z tilde I square, where I is equal to 1 to R, where sigma Z tilde I square is defined as the expectation of the square of the absolute value of Z tilde I. Excuse me. Okay, how do we get this equation? Okay, please see the handout. Okay, please open 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 the handout. Okay, ple and go to page 56. Okay. Page 56, problem 1, derive equation 3.24. Okay. Solution: the signal to noise ratio SINR for the ith eigenchannel is rho I, which is equal to, according to the definition of SNR, is equal to the average signal power of the ith eigenchannel over the average noise power of the ith eigenchannel. Okay. And it is equal to, okay, according to the average signal power, it is equal to the expectation of the square of the absolute value of the signal term and divided by the expectation of square of the absolute value of the noise term Z tilde I. Okay. So what is the signal term? Okay, so equality A results from equation 3.23 of the slides. Okay, let us go to equation 3.23. Okay, in equation 3.23, the signal term is the square root of rho times lambda I times S tilde I, and the noise term is Z tilde I. Okay, so in the absolute value, it should be the square root of rho times lambda I times S tilde I. And in the denominator, in the absolute value, it should be Z tilde I. Okay, because rho, the received signal SNR, is a constant, so rho can be moved out of the expectation. So the square root of rho after taking the absolute value, it is also equal to the square root of rho. Okay, because the square root of rho is greater than or equal to 0. And after taking the square, it is equal to rho. And similarly, lambda I can be taken out of the expectation. So place here, it is equal to lambda I. And according to the slides, the expectation of the square of the absolute value of Z tilde I is equal to sigma Z tilde I square. Okay, we can see the slides. Okay, the sigma Z tilde I square is defined as the expectation of the square of the absolute value of Z tilde I. Okay, so finally we can get this equation for I is equal to 1 to R. Okay, let us go back to the slides. Excuse me. Since Z tilde I is defined as the ith element of U Hermitian times Z, it is possible to show, okay, please see problem 3.3. Okay, in problem 3.3, in equation 3.25, okay, let us go to equation 3.25. Okay, sigma Z tilde I square is equal to sigma square, where I is equal to 1 to R. Okay, let us go to problem 3.3 again. We stated that the variance of the ith element of U Hermitian times Z is equal to the variance of Zi. Prove this. Okay, let us go back to page 56. Okay, the next page. Furthermore, the form of equation 3.21. Okay, let us go to equation 3.21. Okay, in this equation, we stated that R is equal to the square root of rho times H times V times S tilde plus Z. Okay, let us go back to page 57. Okay, so equation 3.21 implies that the square of the Frobenius known of H is equal to Nt times Nr, and sigma square is equal to 1. Okay, because of the normalizations given in equations 3.2 to 3.5. Okay, let us go to equations 3.2 to 3.5. Okay, here. So in this slide, we can see that for fixed H prime, the square of the Frobenius known of H prime is equal to Nr times Nt, and sigma square is equal to 1. Okay, let us go back to page 57. Okay, it follows that rho I is equal to rho times the expectation of the square of the absolute value of S tilde I times lambda I, where I is equal to 1 to R. Okay, how do we get this equation? Okay, because sigma square is equal to 1, so sigma Z tilde I square is also equal to 1. So we can cancel this term. Then we have rho I is equal to rho times the expectation of the square of the absolute value of S tilde I times lambda I. Okay, that is equation 3.26. Using the expression for the capacity of a Seisel channel given in equation 3.13. Okay, let us go to equation 3.13. Okay, in equation 3.13, okay, C Seisel is equal to log 2 of 1 plus rho. Okay, let us go back to page 58. Okay, it follows that the capacity with eigenbeam-forming is given by CEIG is equal to summation I is equal to 1 to R, log 2 of 1 plus rho I, and rho I can be replaced by equation 3.26. That is, rho I is equal to rho times the expectation of square of the absolute value of S tilde I times lambda I. Okay, comparison of this expression with equation 3.11. Okay, let us go to equation 3.11. Okay, capacity is equal to summation I is equal to 1 to R, log 2 of 1 plus rho over Nt times lambda I. Okay, go back to page 59. For CSIR only conditions shows similarities, but also an important difference. Each of the terms in the expression for the capacity under CSIR only conditions depends on the signal-to-noise ratio and the eigenvalue for each eigenmode. Okay, Let us go back to equation 3.11 again. Okay, we can see that this equation 3.11 okay, is the capacity for CSIR only. Okay, so in each term of the expression, it has the received SNR rho and the eigenvalue of the ith eigenmode lambda I. Okay, let us go back to page 59. Okay, each term in the expression for the capacity in equation 3.27. Okay, we can see equation 3.27. Okay, is this equation CEIG is equal to summation I is equal to 1 to R log 2 of 1 plus rho times expectation of the square of the absolute value of S tilde I times lambda I. Okay, depends on these same quantities. Okay, we can see that equation 3.27 also depends on the received SNR rho and the eigenvalue of the ith eigenmode lambda I. Excuse me. Okay, except that each term also depends on the variance of each transmitted symbol. That is, on the expectation of the square of the absolute value of S tilde I. Okay, we can see that this term is the expectation of the square of the absolute value of S tilde I, which is under the control of the transmitter. The reason for this difference is that under CSIR, the transmit power is assumed to be equally divided between the transmit antennas. This shows that a key part of the eigenbeamforming technique is choosing appropriate powers for each of the R transmitted symbols. In the next section, we discuss how to allocate power optimally among the symbols when using eigenbeamforming. Okay, next let us enter the section 3.5, optimal allocation of power in eigenbeamforming. Okay, first let us see section 3.5.1, the water filling algorithm. For the purpose of this discussion, we denote by Pi the power associated with the ith symbol. That is, Pi is defined as the expectation of the square of the absolute value of S tilde I, where I is equal to 1 to R. Our goal is to find the optimum distribution for the set Pi under the constraint that their sum is a fixed value. Okay, as we have mentioned for the normalization used in equation 3.21. Okay, let us go to equation 3.21. Okay, in equation 3.21, it follows that the received signal vector is given by R is equal to the square root of rho times H times V times S tilde plus Z. Okay, let us go back to page 66. Okay, the square of the forbiddance. Okay, it is 25 minutes. See you next time. Goodbye.